Interstellar visitor Oumuamua could still be alien technology, new study hints. Oumuamua, a mysterious interstellar object that crashed through our solar system 2 years ago, might in fact be alien technology. That's because an alternative, non-alien explanation might be fatally flawed, as a new study argues. But most scientists think that the idea that we spotted alien technology in our solar system is a long shot. And in 2018, our solar system ran into an object lost in interstellar space. The object, dubbed Oumuamua, seemed to be long and thin, cigar-shaped, and tumbled end over end. Then, close observations showed it was accelerating. And if something were pushing it on it, scientists still aren't sure why. One explanation? The object was propelled by an alien machine such as a light sail, a wide, millimeter-thin machine that accelerates as it pushes by solar radiation. The main proponent of this argument was Vero, a Harvard University astrophysicist. Most scientists, however, think Oumuamua's wonky acceleration was likely due to natural phenomena. In June, a research team proposed that solid hydrogen was blasting invisibly off the invisibly off the interstellar object surface and causing it to speed up. Now, in a new paper published Monday, August 17th, the astrophysicist journal Letters, Lobi and Thiem Hong, an astrophysicist at the Corree Astronomy and Space Science Institute, argue that hydrogen hypothesis couldn't work in the real world, which would mean that there's still hope that our neck of space was once visited by advanced aliens, and that we actually spotted their presence at the time. Here's the problem with Oumuamua. It moves like a comet, but it doesn't have the classic coma or tail of a comet, said astrophysicist Darrell Siegelman, an author of the solid hydrogen hypothesis, who is starting a postdoctoral fellowship in astrophysics at University of Chicago. Oumuamua was the first object ever seen flying into our solar system and back out again. That's opposed to most solar system objects that turn circles around the sun, never leaving the celestial neighborhood. Its journey and the fact that it was accelerating suggested Oumuamua, which is estimated to be about 1,300 to 2,600 feet, or 400 to 800 meters long, was a comet. And yet, there was no coma or outgassing detected coming from the object, Siegelman said. Normally, comets come from regions more distant from the sun than asteroids, and ice on their surface turns straight into gas as they approach the sun, leaving behind a trail of gas, or what we see as beautiful comet tails, Siegelman said. The outgassing changes how the comet moves through space, he said. It's a bit like a very slow rocket engine. The sun strikes the comet, the warmest part of the comet bursts with gas, and the gas flowing away from the comet sends it tumbling faster and faster away from the sun. In a paper published June 9th in the astrophysical journal Letters, Siegelman and Yale astrophysicist Gregory Laughlingham proposed that the object was a comet made up partly or entirely of molecular hydrogen. Lightweight molecules composed of two hydrogen atoms, H2. H2 gas freezes into a puffy, low-density solid only when it's very cold, minus 434.45 degrees Fahrenheit, or negative 259.14 degrees Celsius, or just 14.1 degrees above absolute zero, in Earth's atmosphere. Researchers had already proposed the existence of hydrogen icebergs out in the very cold reaches of space. Laughlin and Siegelman wrote in the study, an outgassing hydrogen wouldn't be visible from Earth, meaning it wouldn't leave behind a visible comet tail. The numbers worked out neatly, while a few other substances like solid neon could potentially explain the coma-free acceleration. Hydrogen was the best match for the data. But in their new paper, Hong and the Lobe respond to this idea and argue that the hydrogen iceberg explanation has a basic problem. Comas form when icy grains of dust bump into each other in space and form clumps. And those clumps attract more dust and other clumps. And comets are like snowmen. They survive only as long as they don't melt. The stickiness that helps form comets is similar to the stickiness of icebergs or ice cubes coming straight out of a cold freezer. Leaving an ice cube on the counter for a minute or two, let its surface warm up a bit, and it won't feel sticky anymore. A thin film of liquid water on its surface makes it slippery. Hong and Lobe argue that even starlight in the coldest parts of space would warm up small chunks of solid hydrogen before they could clump up together and form a comet of Oumuamua's large scale. And more importantly, the trek from the nearest giant molecular cloud, a dusty, gassy region of space where hydrogen icebergs are thought to form, is too far long. A hydrogen iceberg traveling hundreds of millions of years through interstellar space would have fallen apart, cooked by starlight. Siegelman said that Loeb's analysis was correct, that no hydrogen comet would survive such a long trip. Hydrogen icebergs don't live that long in the galaxy, he said, and you definitely don't have time to get all the way from the nearest giant molecular cloud. The theory only works if Oumuamua is just 40 million years old, he said. Over that time frame, outgassing could have modeled the comet's oblong shape without destroying it entirely. He pointed to a paper published in April in the Astronomical Journal, which proposed a number of nearby origin points for Oumuamua. The paper's authors didn't nail down the comet's home entirely, which would be impossible, they said. Oumuamua was hardly moving when it arrived in our sun's gravity well, which makes tracking the comet through space tricky. But the researchers looked at what else passes through the Milky Way neighborhood that our sun is now passing through in recent cosmic history. They landed on two groups of young stars, the Carina and the Columbia, moving groups. said Tim Holt, a graduate student at the astrophysicist at McGill University in Montreal and the lead author of the paper in April. They all form around 30 million to 45 million years ago in the cloud of gas that then dispersed. The small dissipated cloud of molecular gas with just a few young stars is just one where hydrogen icebergs might form, Holt said. There are many processes that can eject Oumuamua's type object from young stars in moving groups, like gravitationally nudges between stars in the group planet formation, or as Siegelman and Laughlin 2020 argue, the molecular cloud that create the stars in the first place, Holt told Live Science. All three papers fit neatly together if you assume Oumuamua was a hydrogen iceberg that originated in Corree or Colombia, Holt added. Siegelman and Laughlin idea could work here because H2 objects should have a short lifetime in the galaxy, as Lobe correctly concludes, and the origin in the Corree or Colombia would make it young enough to survive its journey, he said. Lobe, however, disagrees, shortening the distance that H2 iceberg needs to travel doesn't solve the problems we outlined in our paper, because the H2 iceberg would have formed when its parent planetary system formed, billions of years ago. And those eons, the iceberg would have evaporated, he told Live Science in an email. Lobe also said that hydrogen icebergs are expected to come from giant molecular clouds, not parts of space like Corree or Colombia. And he reiterated that no hydrogen icebergs could survive the trek from the neatest giant molecular cloud. Asked if there is a clear leading candidate explanation for Oumuamua's acceleration, Lobe referred Live Science to the not yet released book he authored called Extraterrestrials, the First Sign of Intelligent Life Beyond Earth, due for publication in January.